Good morning, all. Welcome to the second day of our short-term training program on recent advancements in structures and materials. So today we have Dr. P. Revathi. She is currently working as a assistant professor in civil engineering department at Pondicherry Technological University. She obtained a bachelor's degree in civil engineering and master's degree in advanced construction technology with distinction from Pondicherry University. She pursued her doctoral degree in structural engineering from IIT Madras in the year 2006. She is the recipient of merit awarded by the government of Pondicherry for securing highest percentage among women students during BTech in the year 2000. She also obtained Sri Gayatri Devi Award from IIT Madras in 2007. She has published more than 100 research papers in reputed international and national journals and conferences. She has successfully guided 2 PhD scholars and many MTech graduates. Presently, she is guiding 5 PhD scholars in various areas of structural engineering. She is also the author of a book on metrics method of structural analysis. And she is an active member of various professional bodies such as Institution of Engineers, Indian Concrete Institute, etc. and is presently the Secretary of Indian Concrete Institute, Pondicherry chapter. With that, we welcome you, ma'am. Over to you, ma'am.
Good morning, Revathi. Welcome. Good morning, Revathi.
Ma'am, please unmute your mic.
You please unmute your mic. Revathi, can you hear? Hello, Revathi. Hello, Revathi. Can you hear?
The screen வரல.
Hello, ma'am.
Hello.
Screen வரலப்பா.
Disconnected.
அவருக்கு மட்டும்தான் வருது, என்னது வரவே இல்லை.
Yes, Revathi. Now it's okay. Can you hear me? Hello.
Sir, I'm able to hear you. Yes.
Okay.
Now, am I audible, sir? Okay. Then okay. One second, sir. Is the screen visible? Is the screen visible, sir?
Madam, your screen is not visible. Only video is there.
Okay. I'm sharing now.
Yeah.
Okay.
Now it is okay, ma'am.
Now it's okay. Okay.
Just to maximize the window, that's all.
Okay, sir.
Okay now, Revathi.
Okay, sir. So good morning, everyone gathered here. First of all, I would like to thank for giving me this opportunity to be part of this 3-day online STTP on recent advancements in structures and materials. And I thank especially Dr. Babakurian, a great and a good friend of mine, actually a mentor for a group of research scholars at IIT Madras. He was mentoring us, then guiding a group of research scholars of our time. So I personally thank Professor Dr. Babakurian for giving us this opportunity. I could see the level of the speakers in the brochure, and he has taken meticulous efforts in bringing all the experts around the country to give you the maximum recent advancements in the structures and materials. Just to serve the topic, he has taken a meticulous effort. So I thank Dr. Babakurian, and then I thank one and all the participants, then the management of Muthoot Institute of Technology and Science for giving me this opportunity. Okay, so now I'll move on to the presentation of today's online webinar, that is about the steel, concrete, composite construction. Okay. And if you have any queries, you can post me on the chat box, or at the end of the session, we can have a interactive session where we'll discuss one by one questions. Okay. So there are different structural forms which have been evolved from the ancient times. And recently, the structural forms for the tall buildings, because we are now in the process of constructing skyscrapers and other tall buildings, and we should know the structural forms which are being used for the tall buildings. And what are these composite structures? What do you mean by these composite structures? And what are the components? That is, what is a composite slab? What is a composite beam? And what a composite column is? And what are the other structural forms of composite, steel concrete composite forms, like shear walls? We are going to have see a overview of the different forms of steel concrete composite members. Okay, so here you're seeing reinforced concrete framed building, in which you have placed the reinforcement wherever it is necessary. For example, in order to take care of the tensile stresses, you place the reinforcements, and some places like in columns, we are putting reinforcements even to take the compressive loads. And then we go for a casting of concrete, then we call it as a reinforced concrete. And with this, the construction has been carried out to match out the number of stories that is required for the construction of these kinds of RC construction. Okay. But there is some kind of a limitation with respect to this reinforced concrete construction, because when we go for a high-rise building, then only the reinforced concrete columns or the reinforced concrete shear walls will not serve the purpose. When we go for more than 30-40 story, 30 to 40 story height of the building. So in those situations, we are going for a different form of construction called as a composite construction. Okay, so here this is one more construction called as the pre-stressed concrete construction, and this pre-stressed concrete construction is also giving us the freedom of achieving a thin, slender, sleeker members than using the reinforced concrete by the process called as the pre-stressing. Can be a post-tensioning or a pre-tensioning, depending on the application and depending on the requirement from the field, you can do it. But today we are going to see only the steel concrete composite construction. Okay, so these forms are all generally used for tall buildings, that is the skyscrapers, or we call it as the tall buildings. Okay, so before we actually get inside this tall buildings, we'll see what is the systems or the structural forms which are used in the tall buildings. So these tall buildings can be either a cross braced building frame, or it can be an inverted V braced building frame, or it can even be a diagonal braced building frame. Okay, so so these vertical forms are acting as vertical cantilever, and the enormous lateral load which is induced by the wind are carried by these braces, and steel are playing, the structural steel members are taking these lateral loads by means of the lateral bracings. Okay. So these forms are all suitable for load to the mid height of the buildings, or the buildings which are from 40 story to the 60 or 70 story building. These forms are all suitable. And so here it is incorporating internally along with the lines of walls as well as the partitions. These frames, or these braced frames, will have the incorporation internally along with the lines of the walls and then the partitions. Or the other thing is, it can go for a rigid frame structural system. A rigid frame structural system, meaning the connections between the beams and columns are made as rigid, and sometimes it is applicable in RC also, but the connections, the steel concrete, the steel connections, when we are making it as rigid, and they slightly become expensive. So this is another form of a construction that is adopted in tall buildings. The next one is a wall frame, a dual system, where we have a shear wall and then the framed structure. So the shear wall as well as the frame structure interact together, and these two systems, structural forms, are taking up the sharing the lateral load created due to the wind as well as the earthquake. So this is another form of a construction which is adopted in tall buildings. So this shear wall system is a very well known type of system, and that is even adopted in RCC frame structures. So these shear walls are the lateral load carrying members which are attracting the lateral forces due to the seismic event as well as due to the wind forces. So this one is the tube structural system. So the exterior columns and beams, they are placed in such a way that they create a rigid frame, and it behaves as if it is like a hollow tube. And we all know the structural behavior of a hollow tube in resisting the torsion as well as in resisting the twisting moment. So this behaves in a very stable manner, and this is ending up with a very good lateral load resistance by various connections. Either it can be rigid or a semi-rigid, and this tube structural system can also be supplemented with necessary bracing and truss elements if the design is required. So it is this type of tube structural systems are used in the construction of buildings up to 60 story. So these are all some of the forms where we have a bundled tube structure system or a trussed tube structural system. For example, the tube in tube construction again has been given or provided with the trusses along the tubes, so that the system is becoming much more stable in resisting the lateral load resistance. Now, with that introduction on the tall building configuration, what is a composite structure? Generally, what do we call it as a composite, or when do we call a material a composite, which is made up of more than two different material? So that is called as a composite. So here the composite structure, here it means, I don't mean the reinforced concrete, because reinforced concrete is also having two material. One is your reinforcing steel, other one is the concrete. So here it is, I'm talking about two different structural forms, One is that it is referring to the concrete, or I mean the reinforced concrete structural element, and other one is referring to the structural steel element. So the parts of these composite members are rigidly connected such that there is no relative movement can occur between these two members. So that is called as a composite structure. So the definition states that the composite construction is within the context of buildings and other civil engineers that implies the use of steel and concrete, which are formed together into a component in such a way that it is resulting in an arrangement which is functioning as a single item. So you have a steel component as well as the reinforced concrete component, and these two will behave as a single unit or a single item, and that component or that structure is called as a composite structure. So here the aim of combining these two structural forms is to have a higher level of performance than that would have been the case with two different materials function separately. All of us know that reinforced concrete, it is a concrete as a whole is a good in taking any amount of a compression, or we can design the reinforced concrete to take a good amount of a compression, but in tension we have to rely upon the reinforcement, and when the tension in the reinforced concrete is exceeding a certain limit, then again those members cannot be designed in a reinforced concrete. Then we go for the taking the help of the structural steel. And again, with respect to the structural steel elements, when they are put under compression, then there is a heavy chance or a larger susceptibility of undergoing buckling when the slender structural steel members are under compression. So one is going to complement each other. That is, the structural concrete is going to complement to the structural steel, so that this structural reinforced concrete and the structural steel are behaving in a unite manner or in a single phased manner. So here the composite structures are having many advantages. That is, it is effectively utilizing steel as well as the concrete. Both the material, the structural steel and concrete, are effectively utilized in this composite structures. Hence, it is ending up in a more economical steel section in terms of the depth as well as the weight, and therefore compared to a structural steel element, if we are taking the advantage of the compositeness of the reinforced concrete and then steel, we can have a more economical steel section. So for example, you mean to have a roll section as an I section for the beams, and top of which you may have the concrete slab, a cast in situ, or sometimes the precast concrete slab. When this concrete slab, which is lying on top of the steel beam, is considered to act monolithically with the steel beam, then there is going to be adequate reduction in the depth as well as the weight of the composite beams. Next one is the enhanced headroom due to reduction in the construction depth. For a given span of a building, if it has been designed with a composite beam, then there is going to be a therefore is going more headroom, and because of that your construction depth is getting and no formwork is necessary. So the previous work with respect to acting form shutting and other things, the composite action of steel as, and there's going to be due to the composite action of the concrete. The amount of is due to the composite action, and due to that there will be less deflection span or given we can decide or we can composite structure more lesser more efficient in arranging the cover to large column free space. And so if it's a normal reinforced we wait for floor or proceed with the further construction in the upper story levels. Whereas in case of structure, the columns in steel and this can be erected, and a steel platform you can go for casting the water. Simultaneously the columns and beams upper is which is giving us the
sorry to interrupt you. Actually, your voice is breaking, ma'am. I think you can switch off your video and just present the PPT only.
Okay, okay, sir. So this is, now is it okay, sir?
Yes, yes, ma'am. Okay, okay.
Okay, okay. So the encased steel beam sections have improved fire resistance and then the corrosion. So here this encased steel beam sections are nothing but your structural steel beams will be encased with the concrete in order to have the fire resistance and in order to protect the steel beams from the corrosion. So hence this is going to serve a dual purpose of serving a composite beam as well as a improved fire resistant members than that of the structural steel members. Okay. So this is another advantage of going for a steel concrete composite beams with efficient material use and protection from the lateral torsional buckling, and shallow steel beams is enough to mean the more headroom, and because of that we have the increased construction space and there will be increased floor stiffness and inertia, and it is a better integrated system unlike the independent steel beams. So no formwork is required. I'll come to you why the no formwork is required for these cast in situ slabs. I'll come to you. And shoring can be avoided. Unlike your concrete construction, the entire shoring and shuttering can be avoided. Now, I'll talk about a composite decks or a slab or a floor. Okay. So composite slab. So this picture is showing you what is called as a So this is the diagrammatic representation of a composite slab. So here at the bottom, you can see a structural steel beam, which is supporting the slab. And then you can see this smaller or a thin metallic sheet shaped metal form. They are called as your steel forms. And this is acting as a permanent formwork. So cast in situ concrete is poured on top of this metallic decking. So this metallic decking is serving as a permanent formwork. So you don't need any temporary shuttering or a shoring when we are going for the casting of these concrete slabs. And there will be some form of a minimum reinforcement in the form of a welded mesh for just to protect the cast in situ concrete from crack, and then to have a transverse load distribution and for a minimum fire resistance. These slabs are designed as a fire resistance in terms of 30 minutes, that is a half an hour fire resistance, or a 60 minutes fire resistance, or 1.5 hours fire resistance. So depending on the fire resistance, the fire rating that is required, the thickness of the slab can be designed, and this is going to provide us with the stiffer concrete slabs as well as a material which is going to have a longer fire rating. So here the components that I want you to see here are your cast in situ concrete, then the minimum welded mesh reinforcement, then the metallic decking. In addition to this, you see an element, and they are called as the shear connectors. So these shear connectors are very important elements in steel concrete composite construction, and they play a major role in transferring the longitudinal shear between the concrete and then the steel. So these are all nothing but the shear connectors. There are different forms of shear connectors available in the market, and we can decide on what type of shear connectors to be used. But more often, these studded shear connectors are more commonly used in practice because they are also more available in market, as well as they are very easy to install in the site. Hence, the headed shear connectors are more popularly used in the steel concrete composite construction. So these shear connectors, they are the ones which are going to play a vital role in integrating the concrete floor as well as the steel beam, which is there at the bottom. So this picture is showing you can see that there are vertical steel elements, and then the beams are also running. You can see the main beams as well as the secondary beams, and top of these main beams and secondary beams, you can see this metallic decking which are placed, and you can also see here the shear connectors which are placed at the regular intervals as per the design requirement, and top of that the concrete will be poured. And you can see here this metallic decking is serving as the permanent platform for these concrete floors. So these composite slabs, you can have different types of the profile sheeting. You can have different types of profile sheeting. The profile sheeting can be either a trapezoidal profile. You can have the trapezoidal profile like this, or you can have a dovetail profile. Or dovetail profile is also called as a re-entrant profile. Either we can use a trapezoidal profile case of a sheeting or a dovetail case of a sheeting. So the manufacturer will give you what is the load carrying capacity or the plastic moment of resistance of each and every product that he is manufacturing. So this picture shows you some of the standard metallic decks available in the market. For example, multi-deck 60 means that the depth of this profile is 60 millimeters, and then so this 323 is nothing but it is giving you the one geometry or one wavelength. So at every 323 millimeters, the same geometry will repeat. That is what is that one wavelength of this profile. So similarly, we can have either a 60 mm deep or a 40 mm deep or whatever it is, depending upon the fire rating that is required for the design. So here, this picture is showing you a metallic shooting guns. Like you have a welding guns. These are all the metal shooting guns, which is useful for installing the metal shear connectors or the studded shear connectors with the headed studs. So it is like you shoot it at a regular spacing intervals, and this shear connectors will be placed on top of the flanges of the steel beams. So it will pass through the metallic decking and then it will be placed on top of the steel beams. Okay, so the thickness of these metallic steel sheetings will be only in the order of 0.9 millimeter to 1.2 millimeters. The thickness of these sheetings will be in the order of 0.9 to 1.2 millimeters. So they are very, very thin metal sheets, but they have the moment of inertia is higher due to the folded forms. The moment of inertia is higher. Hence, it is able to serve as a permanent formwork for placing the fresh concrete on top of it. And here you can see that the space provided below the metallic sheeting can be used for taking up the service ducts. And here the decking with the profile sheeting is of two types. That is, the ribs of the profiles can run either parallel to the beam, or the ribs of the profiles can run perpendicular to the beam. So we have a main beam as well as the secondary beams. So on this orientation, we can have either the profile decking running parallel to the beams or the profile decking running perpendicular to the beams. So there is going to be a difference in taking up the depth of the beam when the profile is running parallel or perpendicular to the sections. So here the entire depth, this full depth of the concrete slab can be considered when the ribs are running parallel to the beam. Whereas when the ribs are running perpendicular to the beams, you cannot ensure that the entire depth of the fresh concrete or the entire depth of the concrete slab is participating in the composite action. So there is a reduction factor given in the code of practice in order to accumulate or in order to account for this ribs which are running perpendicular to the cross sections. So the design has to be done accordingly, whether the ribs are running parallel or whether the ribs are running perpendicular. Accordingly, the beams have to be designed carefully. Okay. So these are all the other forms of composite beams. See here you can see a encased I section. So this is a simple structural I section. It can be a rolled section or it can be a fabricated section, and that has been encased inside the concrete. But this is a completely encased section, and here this is a composite section with the slab. You see here this on top flange of the steel beam, you see the concrete slab is resting and you are placing a shear connector, and this shear connector will ensure a minimum degree of interaction between the steel and then the concrete. So the design of shear connectors are playing a vital role in determining the degree of interaction between the concrete and then the steel. So as far as possible, we are trying to make 100% interaction between the steel and concrete, but achieving 100% interaction is not practically possible, and that is also not economical. Hence, we go for a partial interaction, or we go for a concept called as a partial interaction. So here the degree of interaction is defined as the number of shear connectors provided to the number of shear connectors required for 100% interaction. For example, for a span of 5 meter, if the shear connectors, number of shear connectors required are 20, and if the number of shear connectors provided are only 50, then 15 divided by 20 into 100 will give you the degree of interaction or the degree of shear connection between the concrete and then the beam. Okay, so it is always preferable to have a partial shear connection in order to have a economical design. And a code is also giving us some minimum degree of interaction to be followed. So depending on the connections as well as depending on the structural forms, a minimum degree of interaction is also proposed in the code. I'll come to the codes, Indian codes and Euro codes later. So this is another partially encased section without the slab. You see here, this dark one is your structural concrete, and this web portion is filled with the concrete, and this is your shear connector, which is placed in the web portion, whereas here you can see the shear connector is placed on the flange portion, and here the shear connectors are placed in the web portion to have a proper interaction between this concrete and the structural form. So this is one picture which I already discussed, how we are placing the studded shear connectors. Okay, so here this is an pictorial representation of giving what is the elastic behavior of composite beams. For example, you consider that you are placing two beams of dimension B and H, one at the top and other at the bottom. You see here, it is a simply supported beam with two elements, one at the top and one at the bottom, which is subjected to uniformly distributed load. The total load is capital W. Okay. So here, suppose if there is no interaction between these top and the bottom beam, if there is no interaction between these two beams, then this top material and the bottom material will have no interaction, and due to that, if I try to plot the bending stress, so this dotted line, the dotted line would be the bending stress distribution in the top beam, and here the bottom line, this would be the bending stress distribution in the bottom beam. So here this dotted line is the representation of the stress distribution when there is no interaction. So here you can see that then you have two neutral axes, one for the top beam, another one for the bottom beam. So here the top fiber of the top beam is in compression, whereas the bottom fiber of the top beam is in tension, and whereas the top fiber of the bottom beam is in compression and the bottom fiber of the bottom beam is in tension. So here at this mid height or at this interface, you can see that compression and tension exist. That is, the top beam is under tension, whereas the bottom beam is under compression. So you have two neutral axes, one for the top beam and one for the bottom beam in case there is no interaction. But in order to have a complete interaction or in order to have a monolithic composite action, we have to see that the entire beam, the entire depth of the beam is not breaking, and it is going to have a continuous bending stress distribution as shown with the thin, this line, this thick line. That is the representation for full interaction. The full interaction will have a bending stress distribution like this, which is having only one neutral axis, and the portion above the neutral axis will be in compression and the portion below the neutral axis will be in tension. Okay, so and again this picture is representation of the shear stress distribution. So this dotted lines are the shear stress distribution in case of a no interaction between the top and the bottom beam, and this thick line is the shear stress distribution of the composite beam. Composite beam, I mean there is no slip between the top and then the bottom beam. There is no slip. That is, slip is nothing but the lateral deformations or the lateral movement at the interface of the beam. The lateral movement at the interface of the beam, and there should be no slip between the top and bottom beam. If the slip is minimized, then we can achieve a composite action. But strictly speaking, the slip cannot be minimized to 0. So we have to live with a certain degree of slip. And that is also going to give you the definition for the degree of interaction or the degree of compositeness. So suppose if there is going to be a elastic behavior of the composite beam, then the maximum bending stress is given with this 3/8 WL square by BH square, and the shear stress is given by 3WL by 8BH. I think with the basic of your structural mechanics, am I audible? Okay, there was some problem in between, I thought.
Your presentation is not visible.
Okay. So other types of composite beams which are generally adopted in practice are the simple connections with the roll sections, or when the roll sections are not enough.
Ma'am, your presentation is not visible.
Presentation is not visible.
Yeah.
1 second. Now is it visible?
Yeah, ma'am. Yeah.
Okay. So apart from the composite beams with the rolled sections, we can also go for a composite beams with the fabricated sections, or with the haunched beams, or with the parallel beams, or castellated sections, and other kinds of stub girders and composite trusses. So this is a simple construction with the rolled section. So the rolled sections which are available in the market are used as steel beams, and top of which you place the concrete, and provide shear connectors in order to serve the composite action. And these are all the simple connections with the rolled sections. Okay. So these are all more suitable for the spans ranging from 6 to 10 meters. And they require secondary beams at every 3 meters center to center in order to serve the design. Okay. So next thing is we can either go for a fabricated sections. A fabricated sections can be either a straight tapper or a semi-tapper as shown here. It can be a straight tapper or a semi-tapper or a crank tapper or a stepped beam. So with this, we can go for a fabricated sections when the roll sections available in the market are not meeting to the demand. So with this fabricated sections, we can go for we can achieve economy in the design, but only thing is we have to order these materials to the shop and then we have to procure it. So that would increase a bit of the construction cost. So these fabricated sections are more suitable for the spans above the 12 meters, and there is a significant weight can be saved due to the cranks and then the fabrications. So this picture shows you how the crank sections or the fabricated sections are used in spanning larger spans beyond 12 meters. So this is haunched beams, or you can have two different types of haunches. Either you can have a tampering or you can have a stepped haunches, something like this. So this picture shows that you have a haunch section with the tapered haunching, and this is suitable when we go for a moment resisting connections. So when the simple beam connection is not economical, then you have to go for a moment resisting connections. So under these moment resisting connections, you can go with the haunch sections in order to go with the reduce the construction, the connection cost. And next one is the parallel beam approach. So here this is a simple approach in which instead of running a deeper single beam, we can place two shallow beams parallelly. Instead of running one single deep steel beam, you can have two shallow steel beams, and that is again going to serve the practical purpose. That is, the design is also going to be served, as well as you will end up in having a more headroom space. You can end up in having a more headroom space. Next is the castellated sections, which are from the cold form steels. You can have these castellated sections with either a circular openings or any other shape of openings, and these openings can serve as a service ducts for any service lines, electrical lines or AC lines or any other lines. These openings, web opening, can be taken as a service ducts. So this is a castellated section with a web circular web opening. Okay. And here you can also go with the precast slabs. You can also place some precast slabs, or it can be post-tensioned or a pre-tensioned slabs, and then some concrete is placed, in situ concrete is placed in the joints alone, and that is going to serve the monolithic action between the concrete slab and then the steel beam. So these are all some of the pictures where the composite beams are all adopted. So here you can see that the structural forms, that is the metallic forms, are acting as the permanent formwork. You see that people are standing over it, and the concrete pumps are all placed here, and some concreting is going on. So you don't need any temporary shuttering. And here again, you see that this pipeline is pouring the concrete, and you see some people are standing on that metallic forms without any disturbance. Okay, so with that introduction with the composite beams, now we will see what is called as a composite columns. Composite columns. So here, this picture is showing you a composite column. That is, there are several forms of composite columns available. The first one is a concrete filled hollow tubes. You see a hollow tube here. The hollow tube can be either rectangular, square, circular, or anything like that. So this can be filled with the concrete inside, and this is acting as a composite column. So therefore, this is one of the concrete filled hollow sections. And sometimes you can also go with a fully or a partially filled concrete columns. So this is an example for an partially filled concrete encased columns. So this I section is the steel member, which is acting as a structural steel column, and the web portion is filled with the concrete. The purpose of this is, the first purpose is to serve the required degree of fire resistance. The required degree of fire resistance can be achieved only when you are filling up with the concrete, and even the corrosion resistance is also obtained just by filling it up with the concrete. So it is going to serve the dual purpose. The first one is it is giving the structural stability against buckling of these webs and flanges, and it is also going to give a structural stability against the fire resistance. So this is one particular form which is popularly used in practice. The next form is that you have both, that is the web as well as the flange of the I sections are completely filled inside the concrete, and it is also provided with the reinforcement. It is also provided with the reinforcement or reinforcing steel as like you have it in the regular RC columns. And here this is one cruciform kind of a section filled with the concrete. So there is a large variety or a possibility of configurations or possible configurations available in the composite columns. So here you see some examples of the composite columns or the types of the composite columns given in the code. And here I would like to mention that a large research is going on under this concrete filled composite columns with different forms of steel as well as with the different forms of the columns. Okay, so here one of the researches with respect to the double skin layer concrete filled columns. You have one tube as well as another tube inside, and this tube inside may be sometimes kept as hollow, and so that you have a thin layer of concrete around the core, and the inner core would be left empty. And how to design such a steel in tube columns is a complete process under research. So here you have a stiffened CFST columns, that is concrete filled steel tube columns. You have a stiffness here inside, and then there is a greater advantage of providing this stiffness inside. Okay. So already the steel tube which is lying outside is giving an enormous amount of confinement to the concrete which is placed inside, and due to that the compression carrying capacity of the confined concrete is enhanced by 10 to 15%. In addition to that, if the stiffness are provided inside the tubes, that is again adding up to the increased stability in composite action as well as the increased load carrying capacity. And the ductility of such composite filled columns are so high, and hence the composite filled columns are much more suitable in designing the frames which are under the zones of seismic actions. So this is what I told you, the double skinned CFT columns, concrete filled tubular columns. So you have one outer steel tube and another inner steel tube, and this annular space is filled with the concrete, and this inside core is left hollow only. And here the idea is these two tubes are confining the annular concrete, and this confinement is able to give or achieve a larger stability as well as the load carrying capacity. Okay. So the tubes can be either square inside the circular tube or circular inside the square tube, or we can have any combination of such a double skinned CFT columns. Okay, so the application of the composite constructions, it can be applied in any kind of a commercial building or industrial building, any buildings. But these buildings, these applications of composite construction is not so popular in Indian scenario. It is because that there is a lack of awareness as well as the lack of standards with respect to Indian scenario. As far as India is concerned, like we have IS 11384. IS 11384 is the only code which is discussing about the steel concrete composite connections or the steel concrete composite construction. Okay. So this code is able to give only about the design of shear connectors, the two for beams and then the slabs which are having no degree of interaction or for having a complete degree of interaction. So the code is giving only the limited options, or the guidelines are only limited with respect to the Indian scenario. Hence, the steel concrete composite construction is not so popular in India. Whereas in other countries, this steel concrete composite construction is so popular. For example, Eurocode 8 is talking extensively about the design as well as the construction of steel concrete composite buildings. Similarly, AASC 318 reference 5 is also giving you a different kind of a solution for steel concrete composite buildings. And there are other standards available, like in Singapore and Korea also, different standards are available. But the Indian standard is giving only a very, very limited guideline, and that is not a complete guideline available in India. But I heard that this IS 11384 of Indian code is getting revised, and there are good number of guidelines available, going to be available with us also. Okay. So based on the Indian code guidelines available, let us discuss what are the different types of the shear connectors. Because the shear connectors are the members which are responsible for providing composite action between the concrete and then the steel elements. So the shear connectors are broadly classified into three types. According to the Indian standards, they are broadly classified into three types. First one is a rigid type and flexible type. The third one is a bond or an anchorage type of the shear connectors. Okay. So here we'll see one by one what is a rigid type and then the flexible type. Okay. So rigid type shear connectors, these connectors are very stiff and they sustain only a very small amount of deformation while resisting the shear force, and they derive their resistance from the bearing pressure on the concrete, and finally they fail due to the crushing of the concrete. It is something like a similar analogy I can give, like a over-reinforced beam. Over-reinforced beam, finally the failure is due to the crushing of the concrete, and the steel reinforcement would not yield, as well as it won't undergo any large deformation before failure. A similar kind of analogy is applicable here in this steel shear connector or the rigid shear connectors. So this is This picture shows an example of some rigid connectors. This I have taken from IS 11384 Steel Concrete Composite Construction Code, that is Indian Steel Concrete Composite Construction Code. So here you see this is the top flange of the steel beams, and on the top flange of the steel beams, either you can place a T section and weld it on the top flange at the required interval. You have to design and then say what is the required interval of these rigid connectors. This is one of the rigid connector, that is the T section, which is being welded. See here the elevation of the section is welded at the bottom. And the next one is a channel section. You take a piece of a channel section and then place it in this format and weld it all around the channel section, and that is also going to act as a shear connector. Or else we can go with the built-up sections. We can go with the built-up sections with the either a combination of a bracket and then the angle sections like this. You can go for either a single bracket or a two brackets with the built-up section and then weld it on top of the I section or the steel beam, and they act as a rigid connectors. Apart from these rigid connectors, we have a flexible type of a shear connector, and as the name it suggests, they are flexible by itself and they sustain a higher deformation while resisting the shear force, and they derive the resistance through bending. They undergo a large deformation before failure, and they fail due to yielding of the connectors, like similar to your under-reinforced beam. Similar to the under-reinforced beam, like the under-reinforced beams will undergo a large deformation before failure due to yielding of the steel. And similarly, here the failure is due to the yielding of the connectors. Connectors are made up of this steel and they undergo a large deformation before failure, and they derive the resistance through bending, and they sustain a reasonably higher deformation before undergoing the failure. And this is called as a flexible shear connectors. Predominantly, flexible type shear connectors are used in practice. So this picture again I have taken from IS 11384, the code of practice for steel concrete composite construction. So here you can see that the channel sections, only one side of the flange of the channel is welded on top of the steel beams, and you are placing it at regular intervals or the regular design intervals, and this is acting as a flexible shear connector. And this top picture is the studded shear connectors, which are more commonly used in practice. And these are two examples for the flexible shear connectors. Okay, so the third one which I told you, that is a bond or an anchorage type. So this shear connection comes out from the bond between the fresh concrete and then the metallic decking, or by means of any anchorage mechanisms. You can have any type of an anchorage mechanism, like you have a cables or a bonded wires. I think the slides are repeating. Let me pass. Okay, so these are all the major codes which are available for design of steel concrete composite buildings. So here IS 11384 1985, now it is being currently revised. Only the draft version is available, and that too, that draft version is not available in public. It is only with the committee it is available, and there is a process of, it is under the process of revision. The Eurocode 4, EC4 2004, it is giving you the complete guidelines on the design of steel concrete composite elements. So there are lots and lots of lacunae in the Indian standards. It is talking only about the simply supported beams, and the two beams without any metallic decking, and the two for the beams with a 100% interaction. Achieving 100% interaction is not possible practically. So we have to depend on this Eurocode or AASC 360, that is the American standards 360 2010. Either we can follow Eurocode or the American standards as of now. Once the revised version of IS 11384 has come out, then we can follow our own Indian standards. The next form of the steel concrete composite is the shear walls. So this is another major area of research which is undergoing, in which you go with the composite, steel concrete composite shear walls for a larger, for a taller buildings. So this picture shows how much of the reinforcement is placed inside the concrete shear wall. And top of that, we have to pour concrete and see that the concrete is getting inside these intricate spaces, and then you get a reinforced concrete shear wall. So with this kind of a mechanism, or with this kind of a detailing, it is better to go with the steel concrete composite shear walls, so that we achieve economy in the design. Okay, so here this is the representation of the steel concrete composite shear wall. So here you have, this is one piece of a metal, this is another piece of the metals, and these two pieces of the metals are placed together by means of a tie bars, which are welded inside the metal pieces, and you have the steel headed shear studs either placed on both the metallic pieces, and then you can have an embedded plate for commodity attachments and other things, and you can have a pipe sleeve for penetrations through the steel concrete composite panels. So these panels have to be customized according to the requirement, according to the configuration of the building, and then you place it in position and pour the concrete in between them. And this is another form of a steel concrete composite construction. So here you can see, for example, you have the rebars, then you place the concrete, that is your foundation, and then you see, instead of that reinforced concrete, putting such a huge number of rebars, and then seeing that there is improper compaction between the steel and then the concrete, it's better we can go for the composite shear walls, where we can place only steel plates embedded with the concrete, or we can have some kinds of the headed studs on both the faces of the steel plates and pour some self-compacting concrete. So this picture shows you a comparison of how the construction activities is going to be there for a RC shear wall and then a composite shear wall. So the rebar arrangement itself will take about 13 days in case if you want to erect an RC shear wall. Then you have a wooden forms, then you are placing the concrete, then you have to see that you take out the wooden forms after a minimum of 4 days, then you cure it, then you are put under the structural use. Whereas within 10 days, we'll be able to place this steel plate inside, do all kinds of welding, and then pour the concrete, that's all. So within a maximum of 14 days, you'll be able to complete the entire task. Whereas for the construction of a RC shear wall, it is taking about 28 days. Whereas the composite shear wall, the construction time itself is only 50% of the RC shear wall connection. So you can have speeder construction, and you can also have economy in construction while we adopt the steel concrete composite shear walls. So these are all the some pictures where we have the steel concrete composite shear walls. This can be fabricated and taken to the site, put in position, erected in position, then pour concrete and leave it. The other form is a composite truss. Composite truss, where instead of the beam, which is structural steel beam running at the bottom, we can have the trusses running at the bottom, and these trusses will support the concrete slab at the top. Excuse me. The next application is the composite bridge. You see the steel girders, or you can see the box girders, which are made up of steel, and on top of these steel girders, which are box girders or I sections, on top of that we can place the steel deck inside by means of a concrete, and that serves as a composite bridge. So this is something into the design. So here IS 11384 is giving some design guidelines without giving reference to the profile decking, and it is also not talking about any partial shear connections. IS 11384 is able to give you some design guidelines, whereas according to Euro code there is a difference with respect to Indian standards and then the Euro code, whereas the Euro code is able to give you a different range of shear connections possible, from partial shear connection to the full shear connections, whereas Indian standard is silent about the partial shear connections. So this is a simple design as per the Indian standards. So here again I repeat, it is very silent about the degree of shear connections. It assumes a full shear connection between the concrete and then the slab. How much more I can take? I have a few more slides on seismic resistant design. How long I can take?
Ma'am, up to 11 o'clock.
Up to 11 o'clock. Okay then. Okay. Then I have 20 minutes. Okay. 10 more minutes.
Yeah, ma'am. Yeah, ma'am.
Okay. Okay. So then I'll proceed with the earthquake resistant design of steel concrete composite structures. These steel concrete composite structures, as far as the earthquake resistant design is concerned, again Indian standards are silent about the earthquake resistant design. Euro code 8 is giving you a complete design concept on how to design the steel concrete composite construction building. So it is adopting three concepts. The first one is a concept A, which is a low dissipative structural behavior in the composite building, or you can have a dissipative structural behavior with a composite dissipative zones, or a dissipative structural behavior with the steel only in the dissipative zones. So this third concept is like something like we are not considering the participation of concrete in the dissipative zones. So which means that the composite structure is something like a steel structure. The composite action between the concrete is not considered in the zones of dissipation. So whenever we design with this concept, then the design which are all applicable for steel buildings are only applicable in the concept C. Whereas in a concept A, where there is a low dissipative structural behavior, and again these forms are not suitable in places of a higher seismic vulnerability. So we have to concentrate much on this concept B, where the dissipative action is expected from the composite action or from the composite behavior of both steel and concrete. there is a range of the behavior factor which is given in the composite behavior, which is given in the Eurocode. So like you have the response reduction factor, like we have the response reduction factor in Indian standard. There is a behavior factor Q given in the Eurocodes for seismic resistant design of composite sections. So the structure is classified as a ductility under some ductility classification, either a low ductility or a medium ductility or a higher ductility. If it is a low ductility classification, then the behavior factor is taken a value of 1.5 to 2. And again, there are some configurations related issues, and depending on these configuration related issues, there will be a still further reduction in the behavior factor. But at any point of time, the behavior factor is not taken less than 1.5. And for this medium ductility as well as for the high ductility classes, you can have the behavior factors between that is less than or equal to 4, and it is again limited by means of the various structural forms which are given in the table 7.2 of your Eurocode. Okay, so in a composite structural dissipative action, the capability of the parts of the structure to resist the quick action is through the inelastic behavior, and so the concrete as well as the steel, the inelastic action of the concrete and the steel are taken into account. So while using the design response spectrum, which is given in the code, the upper limit to the reference value of the behavior factor should be taken greater than the upper limit which is established in the 7.1. That is, the behavior factor can be taken as 4. So in the design rules for the dissipative composite structures, we aim at developing a reliable local plastic mechanism in the structure, and therefore we have to go for a reliable global plastic mechanism dissipating as much as more energy as possible in the earthquake action. So this you can decide based on your pushover analysis. So here the Eurocode is telling us to prescribe the concrete of a grade not lower than C20-25 and not higher than C40-50. This grade C20/25 is nothing but the concrete with a compressive strength of cube not less than 25 and a cylinder not less than cube not less than 20 and cylinder not less than 25. And similarly is C40-50 means the 40 is representing your cylinder strength and 50 is representing the cube strength. And again, the reinforcing steel should be of a class B, that is a medium ductility or high ductility steel whenever we are utilizing this steel concrete composite buildings in the zones of higher seismic actions. Okay, so these are all some of the structural types and then the behavior factors given in the Eurocode. That is, you can go for a composite concentrically braced frames and columns. The columns and beams may be either structural steel or it can be composite steel and concrete. You can go with the columns and beams may be either only the structural steel or the beams and columns can be steel and then the concrete composite. But the braces shall be only structural steel. The bracing should be only of the structural steel. And these bracings, we can have either V bracings in dissipative zones in tension, or we can have a compressional diagonals or any other forms of the bracings shown here. But at any time, if you have the frames with the eccentric bracings, then the dissipative zones in bending or shear links should be provided. So this is very important, that is the composite eccentrically braced frames. The members which do not contain the link may be either structural steel or composite steel concrete. Other than for the slab, the links shall be structural steel. We have to provide the shear links or the seismic links as shown in these pictures, and these are for the energy dissipation under the event of an earthquake. So the configurations used in this can be any link. See here you have provided with the vertical link or sometimes provided with the horizontal link. We can have any provision or any configurations. And again, Eurocode is giving you the guideline on how to design the seismic link for steel concrete composite buildings. But at any cost, these K bracings in which the intersection of the diagonal is lying on a column should not be used. The K bracings, that is, here you see that the intersection is lying on the columns. So it is weakening the columns. So this the columns are not designed as the dissipative members. So therefore, such a configuration with the K bracings should be not used in the steel frames or steel concrete composite frames which are under the zones of seismic regions. And these are all other composite structural systems. And the different behavior factors for the different structural systems given. But this itself is a lecture of its kind, how to detect or how to design the seismic links, etc., etc. itself is a topic of its own kind. So I'm just passing on that due to lack of time. So this seismic links, either a short link, long link, or an intermediate link. And again, guidelines are there how to design these links and for what is the rotation capacity of these links are given. Okay, so with that, I stop my presentation. And any questions, any queries? I would be happy to answer.
Now it's time for discussion.
Yeah.
If you have any doubt, please ask participants. Please unmute your mic and ask your question. Any doubt? Participants, please ask your doubts.
I'm requesting the participants to ask some questions.
I think the topic was too boring.
Okay, madam. I have a question. What about the cost? My name is Rema Devi. I'm working in Muthoot as faculty.
Okay, madam.
What about the cost compared to RCC?
Yeah, cost will be higher compared to RCC if you are applying this kind of a technique for low-rise buildings. But if it is a high-rise building beyond 30 to 40 stories, then the cost will be lesser compared to RCC.
Okay, thank you, madam. Also, codes are available for this composite structures?
Indian code, yeah, Indian code is very silent. It is extensive guidelines are not available from the Indian context, but Eurocode and American standards are extensively giving, and Indian standards are now under the process of revision, and we are expecting the complete guidelines on this construction by 2022, something like that. We are expecting it. The draft version is there now.
Okay, thank you, madam. Thank you.
Revathi, whether any bridges are constructed in India using this concept?
There are few bridges, sir. I have some case studies. In West Bengal, there are some bridges constructed using this concept with steel box girders and concrete on the deck. Bridges are constructed, many bridges.
Okay, thank you. Any more questions?
Ma'am,
Ma'am.
one question in the chat box. How
Yeah,
about
what?
the composite section in foundation?
Yeah, like you have a grillage foundations. You have grillage foundations, no, where you use both the structural steel and then the concrete. That is itself is a composite section for foundation.
Whether pre-stressing is possible for this type of construction composite?
Pre-stressing, actually, these slabs which are precast, they are pre-stressed and placed in position, and the joints are filled with the fresh concrete. Only there the pre-stressing is possible. In precast slabs.
Precast slabs.
Slabs, yeah. Other than that, pre-stressing is not possible in composite construction.
Okay, any questions?
If the questions are not there, you can wind up. Seven.
Okay. So thank you, ma'am. Thank you so much for giving such a detailed session on composite structures. That was really a very informative session. So on behalf of the entire department, I express my sincere gratitude to ma'am.
Thank you. Thank you everyone for your patient listening, and thank you again to Dr. ABAQUS sir. Thank you, sir.
Okay, thank you, Revathi, for your presentation. Nice presentation.
Thank you.
Okay.
Thank you all. So our
Then
next session will
Next
start at 11:30 a.m. Okay,
11:30.
next session will start at 11:30 a.m. and details of the session will be shared to your registered mail ID. Okay, thank you all.
Okay, bye.
Bye, sir.